Alright, so let's take a look at this problem. There's infinitely many solutions to this inverse sine equation. They only want us to find the solutions that are between 0 and 720. I know that on the unit circle there's two values that have a y-coordinate of 0.220 that when I use my calculate, see that point is not going to be on my unit circle. Well, it is on the unit circle. It's not one of the special right triangles. It's not one of the coordinates that I have. Um, I'm going to have to use my calculator. My calculator is going to search for values between negative 90 and positive 90. It's going to return a value in the first quadrant. So let's change that to degrees. And I don't know, a couple decimals. So if I go the inverse sine of 0.220, I have 12 degrees. If I add 360 to that, I'll have a coterminal angle that will have the same sine ratio. But when I add another 360, I'll be above 720. So that's too much. So now I need to use this angle. So to get that angle, I'll go back to the inverse sine of 0.220. See, this angle is also the reference angle. It's in quadrant 1. So if I take 180 minus that reference angle, then I have another answer in regards to this point in quadrant 2. And I can find the coterminal angle to it by adding 360. So there might be a little bit of round off error, but if I take the sine of any one of these angles, say we do that 527, it will be approximately 0.220. It could be slightly different because of round off. Now let's even come to 3 decimals. So I'm getting that exact. If I go the sine of 372.71 again. So these are fairly reasonable estimates. Alright, now this time they want us to write an expression for infinitely many. They want us to be in radians. There's 2 points that have a y-coordinate that's this negative value. When I use my calculator, it's only going to return values that are between negative pi over 2 and positive pi over 2. So it's information about that one. So when let's go to radian measure, and it says to the nearest thousandth, so that's 3 decimals. So if I go inverse sine, alright, so there's one of infinitely many solutions. We'll add 2 pi n in reference to this point and all the angles that are coterminal to there. Now, Let's get the reference angle by just taking the inverse sine of this positive. So there's my reference angle, and I want to add pi to that. So that gets me to that point in quadrant 3 in any angle that's coterminal. So I need both of those equations. And if I take the sine, say, of that, I should get something that's approximately the negative 0.391, and I do. Oops. So I need both of those equations to describe all of the solutions that are possible to this equation. Alright, so let's take a look here. Tangent is positive in quadrants 1 and 3. So there's some point that has a ratio of y to x that's equal to 2 in quadrant 1 and also in quadrant 3. So when we use the calculator, it's only going to search on the right half of the unit circle. If I go inverse tangent of 2, so this is in radians, and then to describe the infinitely many solutions, the period is pi. If I add pi, I'll get to that point. So I'll just add pi in, which will bounce back and forth between those 2 points, picking up all the coterminal angles. So I only need one equation for this tangent. This inverse sine of 7 over 25 is an angle. I'm going to let that angle be called theta, and I'm going to draw a reference triangle. With regards to the ratio of this right triangle, the sine, the length of the opposite leg over the hypotenuse by the Pythagorean theorem. Let's take a look. Is that square root 24? Yeah. Alright, so the cosine of this is 24 over 25. And that's our final answer. Inverse tangent, it's positive, so it's going to be in quadrant 1. Let's make this 4, make it 4 over 1. 4 squared is 16, plus 1 squared is 1, and 16 plus 1 is 17. And the hypotenuse then would be the square root of 17. And the sine of theta, oops, that would be cosine, 4 over the square root of 17 if I rationalize that. So there's our final answer for 32. For 33 it's negative, so I'll put it in quadrant 2. I got that backwards, don't I? Sorry about that. So, by the Pythagorean theorem, 8 squared minus and the square root of that is 7. Alright, so We've called this angle theta, and the tangent of theta is the opposite leg over the adjacent. Let's rationalize that. So there's our final answer for that. The inverse tangent is in quadrants either 1 or 4. I'm going to draw my picture. In quadrant 1, I'm going to look at x as x over 1. I'm going to call that angle theta, so it's asking me to find the sine of theta by the Pythagorean theorem. This hypotenuse is the square root of x squared plus 1, so the sine of theta is the opposite leg over this hypotenuse, and let's rationalize that. So there's our final answer for 34. Let's call this angle theta, and the ratio from cosine 4 over x makes this opposite leg x squared minus 16 from the Pythagorean theorem. So the tangent, so the tangent of this angle theta is the length of the opposite leg divided by the length of the adjacent leg, and there's our final answer for that. Let's make this over 1. X plus 1 over 1, if we call that theta. So what is the sine of theta? By the Pythagorean theorem, we've got, and I'm not even going to bother squaring that out, I'm just going to leave it like that. Sine of theta is that over 1. If somebody did square it out, what would you get? Remember that exponents don't distribute, that this is x squared plus 2x plus 1. And the 1 minus 1 would cancel each other out, so we'd have this as that. But I'm just going to leave my answer like that. Alright, I think that's the last one. So hey, I hope that helps, and I'll talk to you later.